Hi there guys, welcome to this video where we're going to take a look at the solution to a problem in mathematics that I've chosen from this textbook, Statistical Inference, 2nd edition. The authors are Casella and Berger. So I've used this book in another video of mine which I might not have uploaded by the time I upload this video. Nevertheless, there is another video that where I use this textbook. This was one of the textbooks that I used at university. In my first couple of years at university, when I did some of my mathematical statistics courses, really useful book. It didn't really... Probability and statistics has always been kind of a weak point for me. Everybody's got their strengths and weaknesses. Mathematical statistics, I find it interesting, really, really interesting, but it's always been something that I've had to work just that little bit harder at than some of the other aspects of mathematics, particularly pure mathematics, for example. So recently I've been trying to kind of brush up on my probability and statistics, skills and knowledge and things like that. And this was one of the problems that I came across that I decided to have a go at. So it involves combinatorics, it involves probability, but it doesn't involve university level techniques or anything. You don't need university undergraduate level knowledge of probability theory or statistics or anything like that. You just need some skill in, some basic skill really in dealing with factorials and binomial coefficients maybe, and a basic understanding of how to calculate probabilities. Okay, so let's get on with the problem. Let's have a look, and we're on page, what page am I on? Page 39. And it's problem number 17. Sorry, number 18. So if n balls are placed at random into n cells, find the probability that exactly one cell remains empty. Okay, so in other words, we've got 1, 2, 3 balls, A, B, C. Well, I'll just use 3 as an example. And then we've got 3 cells. 1, 2, 3. So we can place these balls however we want in these cells. What we're interested in are those combinations where there's exactly one cell that is unoccupied. Okay, so for example, we might have A and B in here and C in here, and that leaves this cell unoccupied. Or we might have A in here and B and C in here, and that leaves this cell unoccupied. It's those combinations that we're interested in. Okay, so this is it starts out as a combinatorics problem. Okay, we need to find, there's 2 things that we need to find. What's the total number of ways that we can distribute these balls into? So here I've used 3, but we need to extend it to n. What's the total number of ways that I can place n balls into n cells? And some of the cells may be unoccupied, there may be more than maybe several balls in one of the cells, you know, whatever. There's all sorts of combinations. And on the other hand, how many combinations can we have where there's exactly one cell unoccupied? So no more, no less. Okay, so and then we put these 2 bits of information together to get the probability that we need. Okay, so as with combinatorics problems, what you need to do is to kind of extract the form of the problem. It's difficult for me to say exactly what I mean by that, but the specific interpretation of balls, cells is kind of irrelevant in many ways. There's kind of an abstract form to the problem, which if you can get to the abstract form, sometimes that can reveal which formulae you need to be using and things like that. But with combinatorics, you've got some basic formulae that you can refer to, you know, factorials, you know, often in the form of factorials, powers, and binomial coefficients, for example. But you've got to figure out how these formulae are going to go together. So one of the objections that I often get, or one of the things that the problems that people have, so when it comes to A-level students maybe, and they're faced with a combinatorics problem, they'll just expect that there's a formula that they need to use for this exact situation. And that's not the case. Sometimes you've got to adapt the formula, the basic formulae that you know, you've got to really adapt them to the specific situation, because there's just such a variety of different possible situations that you can be presented with. But again, really try to kind of get rid of some of the superfluous information, which you're talking about what the exact situation is, whether these are balls and cells, it doesn't really make any difference, okay? And that's going to play a key role, because actually further down the line, I'm actually going to flip that idea around. Rather than considering these as balls and these as cells, I'm going to be considering effectively these as cells and these as balls, okay? So I'm actually flipping the interpretation around, which might seem like a strange thing to do, but there is a reason why I'm doing that. Because it helped me, oddly enough. So let's have a look then. How are we going to do this? So I've got my notes here. It's a couple of days since I did this, so I need to remind myself exactly. I've tried to make a note of some of the kinds of ideas that I was coming up with. So my idea was to deal with this problem was, instead of so we've got the balls, let's say A1, A2, up to AN. So what I did initially was I thought, okay, if I'm distributing these balls in such a way that there must be exactly one cell unoccupied, which means that there must be exactly one cell which has two balls in it. Okay, and so you've got an unoccupied cell, a cell with two balls, and then all of the rest have one ball, and they can be mixed up however which way. Okay, so I thought, okay, let's assume that these balls have all been distributed, A2 to AN, all been distributed. Okay, and there's exactly one ball. There's either one ball or zero balls in the cells. So these are distributed amongst n-1 cells, and then this one has to be placed in. But there's n-1 options. Now, this for me just seemed a little bit complicated. I actually thought about it in a different way. I thought, okay, rather than think about A1, the balls A1 to AN, I'm going to think about the balls A2 to AN and the space. I'm going to think about a space as an object. Okay, so the objects that we consider don't have to all be of the same type of thing, right? So we've got a space here, and then n-1 balls. And because then I thought what I'm trying to solve in many ways is similar to how many permutations are there of these objects. Okay, so rather than thinking about putting the balls into the spaces, I'm now just kind of rearranging the balls, and the space actually is one of my objects now that I can place somewhere. However you want to think it, you can think about it as a special kind of ball or something like that. It doesn't really make any difference. But now we're just looking at the permutations of these n items. Well, that's n factorial, right? So the number of ways that I can permute these objects is n factorial. Okay, so then what about this other ball, A1? Where can that go? Well, it could go into any of the n-1 occupied spaces, right? I can match it up with any of these objects, but not this object. Okay, so how many ways can I do that? Well, for each permutation, I could assign A1 to A2, A1 to A3, A1 to whatever, up to AN. So there's n-1 possibilities. Okay, so if A1 is my ball, my special ball that I've pulled to one side, and permute these in n factorial different ways, and then the A1, there's n-1 options, n-1 spaces that I can possibly put A1 into. Okay, so then I thought, can I do the same thing with A1, A3 up to AN and the space? And yeah, sure enough, I can commute these in n factorial different ways. But this ball A2 now, I don't have n-1 options anymore, because I've already considered the possibility of when A1 is matched with A2, for example. So if I match A2 with A1 here, I get the same combination, right? A1's in its space, I put A2 in, well, that's the same as the combination putting A2 in and then putting A1 in. I don't distinguish between these two combinations. So I can, in this situation, I can match the A2 up with A3, A4 up to AN. So that gives me n-2 possibilities. So we can see where this is going now. If I've got A1, A2, A4 up to AN and the space, then again I've got n factorial combinations, but now this ball A3, I can't match up with A1 because that's already accounted for here. I can't match it up with A2 because that's already accounted for here. So I can match it up with A4, A5, A6 up to AN. That gives me n-3 possibilities. Okay, so how about if I've got the balls, I've got my space, A1, A2, up to AN-1. Well, in this case, there's again n factorial possibilities. But now, this ball AN, it can't be matched up with A1 because that's accounted for here. It can't be matched up with A2 because that's accounted for here. It can't be matched up with A3 because that's accounted for. It can't be matched up with any of these, in fact. Okay, so this is actually going to be 0 times n factorial. So what we see here then is that I've got the sum n-1 times n factorial plus n-2 times n factorial plus n-3 times n factorial. Let me write it out here. N factorial plus n-2 n factorial plus n-3 n factorial. And then eventually I'm going to get down to 1 times n factorial, but then the plus 0 times n factorial. Well, that doesn't really contribute anything. So what is this? This is n factorial times, it's the sum from 1, 2, 3, 4, 5, up to n-1. The sum of the first n-1 integers. First n-1 positive integers. Well, there's a formula for that, right? It's n-1 over 2 times n. Which this just happens to be equal to n choose 2. Let's have a look. N choose 2 equals, in factorial notation, n factorial over 2 factorial times n-2 factorial, which is equal to n times n-1 over 2. Right? Just cancelling these n-2 factors with the corresponding n-2 factors up here, I'm just going to be left with n and n-1. 2 factorial is equal to 2. Well, that's exactly what I've got here. n-1 times n over 2. It's just n choose 2. So the number of ways that I can distribute these balls, n balls, into n spaces so that there's exactly one unoccupied space is n factorial times n choose 2. But we're not done yet because we need the probability of this happening, which means that we need the total number of possible combinations. Okay, so now let's get rid of that. So now we've got to think, if I've got the balls A1, A2, A3 up to AN, and we've got the spaces 1, 2, 3 up to N, how can I distribute these balls? How many different ways can I distribute these balls? Now this is, if you think about this in the wrong way, it's mind-blowing. Okay, or that's the conclusion that I arrive at. And the wrong way to think about it is putting these balls into the cells, because this could go into this cell, or this one, or this one, or this one. And then this one could go into here, 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 all the way up to here. Then this one could go into here, 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 all the way up to here. So you might have all n balls in one of the cells. Which one? Well, okay, then there's n possibilities. Or you could have n minus one of the balls in one of the cells and then one ball in another cell. How many possibilities are there? And your mind just explodes when you start thinking about the number of possible combinations here. I'm sure that there is a way to directly do that. Okay, I'm not saying that it's not possible. I'm just saying that my brain is not powerful enough to deal with that kind of complexity. So what I did was I kind of flipped things around. I thought, rather than thinking about these as balls and these as spaces, I'm going to think of these as spaces and these as, well, I mean, you can think about it however you want. It's almost like these are or maybe think about it this way. Rather than putting the balls in the spaces, I'm assigning a space to a ball. Maybe that's the better way to think about it. Assigning a space to a ball. This is a much easier thing to do. So think about it this way. Let's say we've got the digits 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I've got 5 spaces. And I'm thinking, how many 5-digit numbers can I form with 10 digits? Or however many digits, okay? Let's just say 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, here I can choose from any of those digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got 10 possibilities. Here I've got 10 possibilities. So it's going to be 10 squared, 10 times 10, 10 times 10 times 10, 10 times 10 times 10, and so on, right? So I get 10 to the power of 5. The point is that at each stage, even though I filled this space with a digit, I've still got all of those digits as possibilities for the next space. And then here I've got all of the digits again as possibilities for this space. Whereas here, if I'm thinking about putting the balls into the spaces, I put this ball in a space and then I've only got these n-1 balls left to choose from. Put another ball in, I've only got n-2 balls to choose from. So at each stage, the number of objects that I've got to select from is changing. Whereas with the spaces, if I assign this space to any one of these balls, then for my next assignment, I can still choose from any one of these spaces again, right? So I've got effectively n spaces here, and I'm assigning each, think about n digits maybe, or whatever, I don't know. I'm assigning to this object here one of these spaces. Then I move on to the next object, but I've still got the same n spaces that I can assign to this object. Move on to the next object, I've still got the same n spaces that I can assign to this object. The form of this, the abstract form of this, is identical to the abstract form of this. So here I've got, this is the number of objects that I've got, digits in this case. This is the number of spaces. So in this case, kind of flipping it around, the number of objects is n. The number of spaces, which were originally the balls, is n. So the total number of combinations is n to the power of n. Okay? So, what does that mean then? That the probability, the required probability of exactly one empty space is equal to n factorial times n choose 2 over n to the power of n. Okay, So I really enjoyed this. That's what we're after, by the way. I really enjoyed this problem for the simple reason that it really tested me. Like I say, probability, combinatorics, things like that. It's kind of a weak spot for me. So it's really testing whether I'm going to be flexible enough to think about this problem in different ways, which is a hallmark really of the problem solving process. Can you reformulate the problem in a different way rather than trying to attack the problem directly, which might be very difficult? Can you kind of flip it around in some way, or just change the interpretation so that it becomes much more clear and in some cases obvious? I wouldn't say that this was obvious, but it became much more clear to me. So I hope you learned something from this video. If there's anything that you're not clear about, please leave a comment in the comments section. This is a very small YouTube channel at the time of making this video. I'd be really grateful if you could hit the subscribe button and hit the like button. If there's anybody out there that you think might benefit from these videos, please forward these videos onto them so that they can get the benefit, any benefit that they might be able to get from these videos. And with that, I think that's enough of me rambling on for now. That brings us to the end of this problem, and it brings us to the end of this video. Thanks very much for watching.